Okay, so lecture 1, oops. Will be an introduction to convex surface theory. Uh-oh. Is there some technique for not breaking? Okay, so the goal is to understand contact 3 manifolds MC by decomposing them along surfaces, by decomposing along what are called convex surfaces. Okay, so but before I do this, maybe I should give you a little bit of an introduction to contact structures, in case you actually don't know too much about it. So today, we'll assume that M is a 3 manifold, so it's compact and we assume it's compact and oriented. Right, and then C will be a contact structure. I.e., a non-integrable two-plane field distribution. So how do I want to write this? This is a two-plane field, i.e., a two-plane field sort of contained in Tm, which is locally given by, which is locally written as the kernel of a one-form alpha, where alpha wedge d alpha is not equal to 0. Okay. So not equal to 0 means not equal to 0 everywhere. Okay. And if C is oriented, then you can assume that alpha is globally defined. So if C is, so we assume C is oriented, right, in which case we have a globally defined, so globally alpha, such that alpha wedge d alpha is not equal to 0. And let's just assume that it's actually positive. Okay. So we'll assume for the rest of the talk, I'm going to assume that C is oriented everywhere, and then it's actually co-oriented in the sense that alpha wedge d alpha is positive. Oh, by the way, if you have any questions, please don't hesitate. Since there aren't too many people here, and I can sort of always slow things. I can talk about less if necessary, so feel free. Okay, so the prototypical example is R3 with a standard contact structure. So where C is given as a kernel of one form alpha, where alpha is given as dz minus y dx. And x, y, z are the standard Euclidean coordinates. So let me sort of, maybe first I'll compute. Kernel of alpha you can quickly compute. There's no dy term, so it's d dy. And then you also have a term that looks like, what is it? d dx plus y d dz. And let me sort of draw you a picture just to get things started. So this direction is the x direction. This direction is the z direction. And then the y direction is sort of maybe into the blackboard. And so as you're going further and further into the blackboard, there are several sort of slices. This will be maybe z is negative, this is z is 0, I don't know, let's say minus 1, this is z is 0, no, sorry, not z, y equals minus 1, y equals 0, and then y is 1. And so what we're going to do is draw what's called the characteristic foliation. So if you look at, so it's a two-plane field distribution. For the most part, you can sort of assume that it's some sort of, the viewpoint I would like to sort of emphasize today is that Xi you think of as some sort of physical field. So at each point in space you have some sort of assignment of a two-plane, right? And then you have some sort of field that sort of assigns two planes at every point in space. Okay, so now what we're interested in is what's called the characteristic foliation, which is Xi intersected with this sort of tangent space, the surface. So let's say you have a surface sigma, then you're interested in is Xi intersect T sigma. This is usually called the characteristic foliation. Usually it'll be a singular foliation, but in this case it's non-singular. So if you sort of figure out what this is like 1, 0, y. So your vector will basically your fields will your characteristic foliation looks like this. So when y is negative, your contact structures are all sort of pointing this way. As you're going into the blackboard, it becomes tangent. It becomes horizontal. So it becomes something like that. And as you're going further in, it'll look like that. Okay, so is this okay? So as you're going in, it sort of does this sort of rotational motion. And just another piece of, so the characteristic foliation is this yellow thing, right? And then each leaf of this foliation, so if you look at one of these, then you notice that this line is everywhere tangent to the contact structure. So your contact structure is like this, so if you take a leaf of this, then it's tangent to the contact structure at every point. So something like that is called a Legendrian curve. So a Legendrian is everywhere tangent to the contact structure Xi. Okay, so this is the definition of a Legendrian curve. Okay, so one of the fundamental theorems is that fundamental and easy theorems is the Pfaff-Darboux theorem, which says that, so Pfaff-Darboux theorem says that every contact structure MC is locally diffeomorphic to this contact structure, this standard contact structure. So MC, maybe I should have put some. Is locally diffeomorphic to R3 with the standard contact structure C0. Okay. So far so good. And in this business, one of the most important things, one of the first things you want to understand is this tight versus over-twisted sort of dichotomy. Tight versus over-twisted. So I think for the rest of the talk, I'm just going to write OT. Okay. So it's easier to define what an over-twisted contact manifold is. An over-twisted contact manifold, so an over-twisted sort of MC is actually one that contains, which has an embedded disk, which is called an over-twisted disk. An over-twisted contact structure so maybe I should have, let me rephrase. So a contact structure C is over-twisted if there exists an over-twisted disk that's contained in it, and an over-twisted disk is an embedded disk, i.e. an embedded disk D such that at every point on the boundary of D the contact plane is tangent to it. So such that for all x in the boundary of D, Tx of D is equal to C at the point x. So, okay, so let me sort of finish this. A contact structure is tight if there's no over-twisted disk. So a contact structure C is tight if there's no over-twisted disk. And so let me sort of draw you, give you a picture of an over-twisted disk first. So maybe I'll first draw this and then explain what this means. So what I'm drawing is the characteristic foliation of the disk. And let's say I sort of actually extend. This is the boundary of the disk. And what you have is a tangency at the very middle. So at the very middle you have a tangency like this. So if the disk is sort of here, you have a tangency at the very middle. And as you go, and this model is radially symmetric. So as you're going sort of radially, it's rotationally symmetric. And so as you're going radially out, you start rotating. Contact structures are non-integrable, so you have to start rotating. You keep on rotating, 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 and you sort of rotate too much, and you go belly up. And then you have a tangency at this point. And then you sort of sweep out something that looks like this. And what you have is a tangency here, and then this is supposed to be a circle of tangencies. So this is a circle of tangencies. So if you have something that looks like this, it's called an over-twisted disk. And if you've never seen this before, it's sort of not so clear why this is why this is an important notion and why this is what's its meaning. And the thing is, even after you've done contact geometry for 10 years, it's not completely clear what this means. So, well, it's a little bit mysterious what this over-twisted disk is doing. Okay, are there any questions so far? Okay. And please feel free to ask questions. Okay. To somehow motivate sort of our discussion of tight versus over-twisted, let's consider a slightly different model for R3. So we have R3 with zeta sub r, right, contact structure. And this time we use cylindrical coordinates. R theta z. And let's suppose we have some sort of r, some real number which is greater than 0, and we write down some sort of contact form, alpha sub r, which is, I'll mess up if I don't look at this, a cosine of f sub big R little r dz plus r times sine f r r d theta. Okay. And the function f sub r looks like the following. If this is the r coordinate, then f sub r, so this is some big R, and this will be some sort of asymptotic height. Okay. And the graph of the function that we want is something that looks like this. So the graph, we have the graph of f of r. This is graph of f sub big R little r. Okay. So initially you want this to be equal to r, right? So you want the function to be f of r equals r. So, and then you sort of want to gradually asymptotically approach something like this. So this is asymptotically approaches big R, and then you want the derivative to be positive. So you want some function, any function that has this kind of property, where this is just some sort of, you need this so that it's actually smooth, because we're in polar coordinates. So you have some function like this, and you write down a form that looks like this. This you probably want to think of as like r d theta rather than d theta. So it's really some sort of term that has a cosine and it has a term that has a sine, and then this r d theta you sort of think of as one unit. Okay, so roughly speaking, what you're doing is almost the same as this. I'm basically writing down some sort of formula for things that look like these. And so you have a tangency at the very center, and as you're going sort of radially out, this big R tells you how much you're allowed to rotate. The R basically tells you how much you're allowed to rotate, so you might sort of stop at when you sort of do R rotation, or you might, if R is like 5 pi, you sort of do like rotate 5 times as you go radially out. Is this okay? So the formula is sort of complicated looking, but all you're doing is sort of doing this kind of picture where as you're going radially out, you're rotating R times along this axis, and it's radially symmetric. Okay, so it's sort of, there's sort of one clear observation. So if R is greater than pi, then there exists an over-twisted disk. Okay. Right. So you just take the disk z equals constant. I'm sorry, the plane z equals constant, right? And then on this plane z equals constant, it basically looks like, right, the characteristic foliation. If it's actually sufficiently big, the characteristic foliation will look like something like that. Okay. So this is clear. Okay. Now, and what happens if R is less than or equal to pi? So, okay, so if R is less than or equal to pi, well, I guess there's no clear over-twisted disk. Okay, so you can try to, right, so if this is, yeah, maybe I won't say, so it actually could be equal to pi because pi is the asymptotic value, so you actually never reach pi. Okay, so the fundamental theorem of the subject, in some sense, without this theorem, there's sort of no contact topology. So I think Thurston in the late 70s actually conjectured that, well, you know, for example, there are certain things which are over-twisted and certain things which are sort of not clearly over-twisted, and the things that are not clearly over-twisted are actually not over-twisted, right? So and then there are sort of a couple of sort of attempts at doing this, and the Bennikin's is, I think, the first one that's actually correct. So that's why his name is here. But then the reason you have a name, the Thurston-Bennikin invariant of a Legendre-Nault has Thurston's name on it, is because Thurston had actually conjectured this fact. Okay, so this is actually, Bennikin's theorem is that this is actually tight if this R is less than or equal to pi. Okay. And one exercise you might want to do if you're sort of bored is that you can show, this is actually an exercise. You can show that this is actually isomorphic to R3 with sort of the thing that I had before. Oh, that has too many squiggles. R3 with C0. Okay, so that was the standard contact structure that I wrote down. And the standard contact structure is actually tight by Bennikin's theorem. So this is actually quite non-trivial. Since then, there have been sort of many proofs of this. But somehow either anything that you want to do by hand, I think, is slightly complicated. Okay, so the reason this is important is that, in other words, right? Every contact structure is locally tight, right? So it has a local neighborhood, right, which is tight. So combined with this Pfaff-Darboux theorem, you know that if you sort of if you take a small enough neighborhood, you're guaranteed that there's no over-twisted disk inside. So let me continue a little bit more with this story, because, okay, so we know that we have something that's tight, and then we have a bunch of things which are over-twisted, right? And, well, you might wonder, so suppose I have one that rotates where r is 3 pi versus r equals 5 pi, or r is like 7 pi, right? Something that rotates once, rotates 5 times, or rotates 7 times, right? And for a long time, people thought, I think it's probably natural to suppose that they're all different. Right? You sort of rotate 5 times, 10 times, and so on. You should actually get different numbers from this. And the really amazing theorem, I think so these days we sort of know what the answer is. But in those days it actually incredible, I think, sort of breakthrough, right? Which is Eliashberg's theorem. So we'll say a little bit about classification. The over-twisted classification by Eliashberg in the late 80s. Incidentally, I don't know if anyone there's actually no really easy proof of this. So it's actually, so people might actually want to think a little bit about how you try to prove this with modern techniques.
Who introduced the notion of over-twisted?
So it got introduced somewhere between sort of Thurston, Benniken, and Eliashberg. So the way it's phrased, right, is due to Eliashberg, but sort of it's, yeah. Okay, so the over-twisted classification says that pi 0 of the contact two-plane fields which are over-twisted, right? So these are the over-twisted contact structures, over-twisted two-plane fields. Okay. That's actually isomorphic to pi 0 of the space of distributions. So just the two-plane fields. Okay, so in particular, okay, so I didn't say this. So in particular, that means that, what was it? R3 with this zeta sub r are all the same if r is greater than pi. So if you're sort of bored, you might actually want to think, how in the world do you get sort of one into the other? This is sort of, it sort of boggles my mind. But okay, so maybe the only other thing I will say about classification is that so you can classify tight contact structures, for example, on 3-ball. That's probably the most fundamental thing, and 3-sphere. And then sort of in general, there's sort of a, coarse classification. Maybe we'll call it. Oh, so in the tight case, so this is. In the tight case, there's some sort of coarse and let's for now assume that the manifold M is irreducible. So suppose is irreducible, and I think I'm already lying, but let's assume that pi 2 of M, i.e. pi 2 of m is actually 0. Okay, so if it's not, then you can you have some sort of connect sum formulas. Then you have the following. So on the one hand, you have if m is toroidal, i.e. there exists an embedded torus T contained in M, such that pi 1 of T injects into pi 1 of M. Pi 1 of T injects into pi 1 of M. And so if we have something like this, then there exist infinitely many isomorphism classes of contact structures. Infinitely many isomorphism classes of tight contact structures. So this is, maybe I should have attributed something. So this one is due to Kolan, and then by myself, Kazez and Matic independently. And then the second one is what happens when you have something that's atoroidal. So this is joint work with Kolan and Giroux. So Kolan, Giroux, and myself. So if M is atoroidal, that's not toroidal, then there exists finitely many tight contact structures up to isotopy. Finitely many tight contact structures up to isotopy. So isotopy just means like one parameter family of contact structures. Okay, are there questions?
So what is the method of proving this finiteness?
Yeah, so the way you prove this is to use, so how do you say it? So first you take some sort of triangulation of the three manifold, and then you sort of put all the contacts, and then you can define what's called a Legendrian contact triangulation, where the edges are Legendrian and the sort of faces are convex, as we will define in a moment. And then you sort of slowly reduce the number of cases and so on until you. What is it? Yeah, it could be 0. So, okay, so that's another way of advertising my theorem. Okay, so there are sort of several examples of maybe there are some people who are sort of interested in hyperbolic things. So while you're asking, the first example of a three-manifold without a tight contact structure was due to myself and Etnayer, which is the Poincare homology sphere with reversed orientation. So sort of maybe a fact is like theorem. There exist three manifolds without tight contact structure. So there's sort of a really short list of things. The first one was the Poincare homology sphere. With reversed orientation. Okay, so this is myself and Etnayer. And then Andras Stipschitz and Liska produced other put this in some sort of into some sort of family, some sort of one parameter family of tight contact structure. So sort of exist infinitely many sort of along these lines. So Liska Stipschitz. Okay. But so maybe since there's sort of a question, one of the sort of questions which still remains unanswered is that does a hyperbolic three-manifold always have a tight contact structure? So does a hyperbolic three-manifold always have tight contact structure? I don't know. Maybe I'll say yes, and then it'll be the Honda conjecture. So. But actually, one thing that you, yeah. So somehow the answer to this question is really, really tricky because you, how do you say it? Okay. So first thing is that oftentimes one way of constructing a tight contact structure is by finding a taut foliation, right, on the three-manifold and somehow perturbing it into a tight contact structure. And there are many manifolds which are known now which are hyperbolic and have no taut foliation. So you're not supposed to do this kind of strategy. And the second thing is that there are also hyperbolic three-manifolds which don't have what are called universally tight contact structures. So universally tight means if you have a contact manifold and you sort of pull it back to the universal cover, that the contact structure that's tight here still remains tight in the universal cover. So there are actually three-manifolds, hyperbolic three-manifolds without this property. So you have to be sort of smart in order to show that every hyperbolic three-manifold either has a tight contact structure. It's easier to show that it doesn't, probably. But okay. Okay, so those are sort of things surrounding classification. And now I would like to talk a little bit about convex surfaces. So the notion of convexity was introduced by Eliasberg and Gromov. So convexity sort of introduced by Eliasberg Gromov. And basically the theory of convex surfaces, the theory that I'll talk about was really developed by Giroux. Okay, so let me first give you some definitions. A closed oriented embedded surface sigma contained in MC is said to be convex if there exists a contact vector field which is transverse to sigma. There exists a contact vector field X which is transverse to maybe I'll just write which is to sigma. So what is a contact vector field? A contact vector field is a vector field so that if you integrate along this vector field, the resulting diffeomorphisms preserve the contact structure. And so that's maybe the first thing. And then once we have something like this, then you can define the dividing set. So the dividing set gamma is the set of points x in sigma such that the x, so the contact vector field lies in the contact structure. Are there some questions? Are there questions?
There will be.
Okay. So by the way, this, at least the theory, the notion of convexity and so on, you can definitely define in sort of any dimension. So you might want to, if you're sort of curious, you might want to like think a little bit about how you define a convex hypersurface that's sitting in sort of an arbitrary n dimension and 2n plus 1 dimensional contact manifold. Okay, so this is the dividing set. At this moment, the dividing set actually depends on the contact vector field. So, right, so let me sort of write some facts that'll maybe start to illuminate a little bit what this sort of dividing set is doing. The first thing is that the dividing set gamma is a multi-curve, i.e. an embedded one manifold. So it doesn't have to be connected, but it's going to be an embedded one manifold in the surface sigma. So you have maybe a surface that looks like this. Dividing curves will always be in red. So okay, so that's the multi-curve. Oh, maybe not just a multi-curve, but an oriented. I'll say a little bit about the orientation in a moment. Okay, so in particular, if you're sort of so what is this? What does this mean, right? You have your surface sigma, and you have a contact vector field which is transverse to it. So let's say you think of it as pointing out of the blackboard, okay, and the contact structure along the surface is not sort of right. So it's non-integrable, so it has to wobble a little bit. And you're interested in the set of points where the contact structure is basically perpendicular to the surface. You're interested in the set of points where the contact structure is perpendicular to the surface, but what does it mean to be perpendicular? So there's no real natural definition, but let's just say perpendicular means the direction given by the contact vector field. So that means, if you write this, then that means the contact vector field is contained in C. So that's basically sort of a set of points which are perpendicular, where the contact structure is perpendicular to the surface. And the second thing you might be wondering is, if you define something like this, why is this some sort of smooth thing? Right? Why aren't there singularities? Why aren't there, why aren't there singularities? It turns out that the contact condition, if you rewrite this, ensures that it actually is a submanifold. And then also the contact structure, the characteristic foliation is also transverse to the dividing set. So this is where you need some contact condition. So that's the first fact. The second fact is that the isotopy class, the isotopy type of gamma does not depend on the choice of contact vector field. So does not depend on the choice of contact vector field X. Okay. So usually that means that I won't put an X. So gamma a priori is dependent on X, but I'm not going to put X until at some point when it actually becomes important. It actually becomes important. Maybe I'll sort of quickly say this. It becomes important only when there's a difference between sort of isotopy and actual representative. And for most curves on surfaces, the space of curves which are isotopic to something is actually sort of, for example, if you're on something that's hyperbolic, it's actually contractible. So there's almost no difference between curve and actual representative. But sometimes it actually makes a difference, for example, on a torus or on a sphere. So anyways, usually I'll assume that it's actually an isotopy class. Okay, and then the last thing is that gamma divides sigma into alternating positive and negative regions, into alternating sort of positive and negative regions. So that is to say, there's actually some sort of, so if this is plus, then it sort of alternates minus, and then you have plus and so on. And then usually the kind of orientation you want to give gamma is it'll be the boundary of the positive region, let's say. So it'll be the boundary of that.
So the improvement 2 and 3 is sort of your length, right?
They're all sort of like
I mean, if you think about the characteristic foliation, that sort of tells you why 2 is
the 2?
Yeah. Is the fact that it has to separate
no, okay, so this one, 2 is actually proved by showing, sort of writing down this, like, how do you sort of generate 2 different contact vector fields, right? So if you have 2 contact vector fields, they're sort of connected by, they're sort of generated by a function, and you sort of interpolate between the functions.
You could
and then
say that you have the characteristic foliation, and the gamma has to separate the positive and negative singularities.
So a priori we don't know this yet, right? So a priori we don't, like, once you start understanding a little bit more about what the dividing set is doing, then you start understanding, like, you have your like, right, for the positive region, sort of the Legendrian skeleton given by the singular points and sort of the connecting trajectories, deformation retracts, is a deformation retract of the region. So you know various things sort of a posteriori, but sort of a priori, the way you prove this is just by taking a 1-parameter family between functions.
What does this plus and minus mean?
Oh, so plus, yeah, okay, so, right, so plus basically means that you have your contact structure, and before you sort of cross the dividing set, you're sort of maybe pointing like this, and after it's pointing maybe like that. And so the question is, if this vector field x gives you an orientation of xi, or if it's actually the opposite of the orientation of xi. So those are sort of, plus means it's the orientation given by given orientation of xi agrees with the normal orientation given by x, and sort of the other way is minus. Well, good. Anyway, so there are many things I'm trying to sort of avoid having to say, but if you ask questions, I will answer them. Okay. So that's maybe all I want to say about this. Do I want to say... Wait, does this last until... What is it? 10:30?
Yeah.
Let me see.
Well, I can ask a question.
What is it?
Well, what I was murmuring to Andras about was that just examples of convex surfaces. When I first learned this, I couldn't, maybe I was being completely stupid, but I couldn't prove for myself the round sphere. Using this definition, it's just a round sphere in R3 with standard structures.
It's not so easy.
It's not, am I right that it's not easy?
It's not easy.
Produce the contact vector field.
That's correct. Yeah, you have to somehow... how do you say it? Like, you have to somehow ignore the fact that it's sitting somewhere that you know and that you're familiar with, right, and just sort of abstractly produce. You somehow abstractly produce a contact vector field. That's probably a better way of doing than. Right. So somehow that's sort of an issue about being able to construct various things locally. So sometimes, like, locally, it's easier to construct them abstractly rather than actually doing hands-on sort of I'm not sure exactly how to do it. So somehow, sometimes it's actually, even for like things that you're familiar with, it's actually better to do things somewhat abstractly.
But the vector field should exist globally. The definition is, or only in the neighborhood.
Okay, so. Right, so that's another issue. So a contact vector field is usually given by a function, which means I can actually damp off the function right outside of the surface, and so it could be 0 outside, and then sort of so it's actually completely local. You can actually, if you choose, you can get a global vector field. Otherwise, you can get you just need a local one. Okay, so they're all good questions. And I want to say, maybe sort of I'll quickly say something about, there's actually some sort of relative case that might get called upon. So a relative case is when you have a convex surface with Legendrian boundary. So convex surface with Legendrian boundary. So you can, under some mild condition, you can sort of still make sense of convex surfaces with Legendrian boundary. And if you do this, for example, if you have a disk, then the kind of so this is for the disk. So sometimes you have dividing curves that look like you have a bunch of points on the boundary, which are endpoints of the dividing set, and you might have things that look like that. So you have things like plus, minus, minus. Okay. Right. So let me state some properties of convex surfaces. The first one is that it's actually generic. So this is only true for a surface. So the first one is genericity. So anyways, basically all these are proved by Giroux. Okay. Is that the C infinity generic embedded closed surface, closed embedded surface is actually convex. Okay. And maybe I'll briefly say a little bit about this. So roughly speaking, you're interested in somehow the C infinity generic characteristic foliation on the surface. So you have your surface, and your sort of contact structure draws some sort of characteristic foliation for you on the surface. And it's this actually sort of depends on two facts. One is sort of a classical theorem due to Peixoto, which says that a C infinity generic vector field is of a certain type called Morse-Smale type. So a C infinity generic vector field on a surface is of what's called Morse-Smale type. It has sort of standard-looking singularities. Right? It has sources and it has sinks, and sort of nothing else sort of besides sources and sinks. And then once you have a C infinity sort of a characteristic foliation of Morse-Smale type, you can explicitly construct this sort of contact vector field. So once you have a Morse-Smale characteristic foliation, what you do is you have a bunch of collection of singular points. Let's say they also come in sign. So we were talking about positive and negative regions. So you have positive singularities and negative singularities, and you connect between sort of trajectories between the positive ones, and then that actually gives you some sort of skeleton. And that skeleton basically is a deformation retract of, let's say, the positive region. Once you have you can construct your the contact vector field X by hand. So maybe I'll just say that. Okay, so I won't say much more, but. So this genericity is quite an important feature, because if you want to start cutting your 3-manifold, suppose I want to start cutting my 3-manifold, then I sort of usually have a surface given to you. And then given a surface, I can sort of perturb a little bit to make sure it's actually sort of convex. So this is actually not true in higher dimensions. So you take any hypersurface in higher dimension, well, it's not going to be convex. Even if you sort of perturb, well, okay, we don't know this, but no one can actually prove that it's not going to be convex, and it's sort of expected that it's not going to be convex in general. So this is a really special feature in dimension. This genericity is a really special feature in dimension 3, and but it doesn't really work in higher dimensions. This is probably
deal with a vector field rather than some higher dimensional singular distribution.
No, like you can try to do something similar, but it's really a question about. It's really okay. So I'm not sure exactly. Okay, so there's sort of one issue. Let me sort of point this out. So it turns out that these things, right? These curves, the dividing curves, are actually so they're transverse curves, right? But then the more proper way of thinking about them is as codimension 2 contact submanifolds. Okay, so you're now starting. You have a surface, and you want to sort of pick something, and you want to say, I want to sort of force certain things to be sort of to have codimension 2 contact submanifolds sitting on various sort of hypersurfaces codimension 1, and this issue about finding codimension. What was that again? Codimension 2 contact submanifolds is actually sort of a non-trivial question. Right? It's not a sort of flexible problem. So somehow in dimension 3, finding transverse knots is really a flexible problem, but in higher dimensions it's not. So this is actually sort of serious. Okay. The second thing is flexibility. By this I mean the following. So you can phrase it in some different ways, but suppose we have 2 contact structures. So exist 2 contact structures, C1 and C2, on let's just say on R cross sigma. So you're interested in some sort of convex surface, and you have some sort of direction T, which is the invariant direction. You have some sort of convex surface, and you're looking at the invariant neighborhood, sort of, which is the T direction, such that we're assuming that ddt is a contact vector field. Okay. And gamma is a dividing set for both. Sorry, is for both C1 and C2, and then dividing set with respect to this contact vector field ddt. So suppose, I don't know how you draw this, but you have some sort of surface, right, and you sort of cross it with R. And the ddt direction is a contact vector field, i.e. the contact structure really doesn't change as you're sort of moving up and down. Okay. And the thing you've prescribed, you've made sure that the dividing set right, so what I'm saying is that the dividing set is actually fixed. The dividing set, for example, I don't know. Right, so the dividing set is actually fixed. Okay, then there's going to be a one-parameter family. So it exists a one-parameter family of diffeomorphisms one parameter of diffeos. Maybe I should just say isotopy, but diffeomorphisms phi sub s from R cross sigma to itself, where S is in 0, 1. Okay. Such that the first thing is that, well, since I said isotopy, it has to start at the identity, and then phi sub s actually does not move. You don't want to sort of right. So it's some sort of diffeomorphism or isotopy of this thing, and you want it to fix the dividing set. So it fixes the dividing. Oh, it's not sigma. That would be boring. On the dividing set, it's actually it's the identity, and then phi sub s sort of commutes with the translation. So commutes with the T translation. So by this I mean whatever you're sending this, you have to be able to translate up and down. And then lastly, phi sub 1 pullback of C sub 2 is equal to, maybe I should have written, sorry, maybe this should be 0 and 1 or something. So given two contact structures with the same dividing set, you should be able to get from one to the other through some sort of simple thing. So maybe a schematic picture is something like, you have dividing curves. This is a side view, and you have some sort of dividing set that looks like this, right? And then you want to fix the place where you have dividing curves, and then just change the surface. Maybe it'll look like, I'm not sure if I can draw the same thing. Yeah, so anyway, something like that. You want to do this kind of operation. So, right. So this might actually sound sort of complicated, but what it roughly says is that the dividing set actually controls all the key contact topological information in a neighborhood of the convex surface. So if you don't like exactly how this is stated, so the key point here is that gamma encodes all of the contact topological information. Oh, okay, so information all of the, okay, let's say essential, just so I can cheat. So essential, I don't really know what essential means, but all of the essential contact topological information in a neighborhood of sigma. Okay. So roughly speaking, I say, well, okay, so suppose I give myself some characteristic foliation which is compatible with this dividing set, then I can go and sort of pick my favorite characteristic foliation which is compatible with this dividing set, and then within a small neighborhood of this, I can sort of realize the same exact characteristic foliation. Okay. Any questions? This is the following. Suppose you have suppose I have a curve on a convex surface. So I have some sort of convex surface, and I have dividing set. Okay, maybe I have something like this, and I pick some curve that I want. My favorite curve. Maybe that. Okay, so I pick a curve C, right, on this surface. And moreover, I assume this curve C has a certain property called being non-isolating. So, okay, such that C is transverse to sigma, transverse to the dividing set, and is non-isolating. Okay, there's some sort of technical condition which says that every component of sigma cut along C actually contains some piece of the dividing set in it, i.e. Gamma, let's say, every component of sigma minus C contains, sort of non-trivially intersects gamma. Okay. So what does this mean? So you have your curve C, okay, and then it cuts this surface sigma into two pieces, the outside and the inside, right? And on the inside, it actually has like certain pieces of red, right? So it actually intersects, and then on the outside, it also intersects the red, so it actually satisfies this non-isolating condition. Okay. So the isolating means, for example, if you have a piece that looks like this, okay, so if you have something like this, there's no red inside. So this is isolating. Okay. Anyway, so why am I sort of interested in this? It's because that if I have such a multicurve, then I can always realize it as a Legendrian curve on a convex surface sigma with the same dividing set. Okay. So then there exists an isotopy phi sub s, sort of as above, so as above, sort of as in this sort of flexibility theorem, such that phi1 of C is Legendrian So you want to use the same kind of sort of isotopy, and you have an isotopy of that type there, which sort of takes C and makes it into a Legendrian curve.
But now it's just a single fixed context structure.
Say that again?
You're not thinking of two context structures.
Right, they're not sort of two context structures, but yeah. Yeah. No, say it again? Yes. So, the thing that's sort of important here is some discussion about twisting numbers. So, the twisting. Let me sort of talk a little bit about twisting number. Right? Sometimes it's called the Thurston-Benneken number. So, and then with respect to the framing of T sigma. Okay. So what do I mean by this? So I have some sort of, now this has been made into a Legendrian, and then the Legendrian, you have some sort of framing of the two, so you have a two-plane field, right, which is T sigma, which gives you some sort of framing along here, and then you're interested in how the the contact structure rotates with respect to this framing that comes from T sigma. Okay. And it always, the thing that's sort of fact is that whenever you cross a dividing set, right, you always rotate this way. So it's actually always a negative twist. So basically what this says is that the twisting number relative to this, relative to the tangent framing, is actually minus 1/2 times the number of intersection points. So this is actually equal to minus 1/2 times the number of intersection points between the curve C and gamma. This is a little bit strange. You don't. The procedure is that you always, every time you intersect, you get a sort of, you pick up a minus negative half twist. Okay. And then what this sort of theorem is saying is that you draw anything you want, and as long as it's non-isolating, you can realize it at the exact same number of intersection points. Okay. Okay, so let me sort of close with the one last fact, which is called the Giroux criterion. And this basically tells you if you're given a convex surface, how do you determine if its neighborhood has if its neighborhood is tight or not. So so a convex surface sigma has a tight neighborhood if and only if one of the two things happens. So if one, sigma is not equal to S2 and gamma has no homotopically trivial component, or 2 sigma equals S2 and gamma is just S1. So this is sort of the exceptional case where you're allowed to have homotopically trivial curves, but it should look like that. Okay, so we're starting to realize that if you're interested in convex surface theory, so if you're interested in contact structures, you first take a surface, and then on the surface you have some sort of contact structure, but you sort of start ignoring the contact structure. You just look at the curves. Okay, so we're slowly starting to do just some sort of topology of curves. Right? So you have a bunch of curves, and then now you start looking at the curves and say, well, do you have some component that looks like this? Right? So if it has a homotopically trivial component, then it's already over-twisted. It has an over-twisted neighborhood. And how do you actually check to see if it actually has an over-twisted neighborhood? You just do this Legendrian realization. You draw this curve, right? So that was already there. And then you now draw a curve that looks like this. Okay. So you draw a curve that looks like this, and, well, you have something inside and something outside. Okay, so maybe sometimes it doesn't, but we sort of ignore this fact. So you have something inside, and then this automatically gives you, so you can realize this as a Legendrian curve, and then the thing inside basically just is an over-twisted disk. Okay. So somehow the presence of a homotopically trivial component is basically the same as the presence of an over-twisted disk. Okay. So that's pretty much it for today. So maybe it was a little bit too easy, maybe it was not. But tomorrow it'll get a little bit more algebraic. And so far we've studied what happens when you have sort of one surface that's in here, and then you have to start moving. If you want to analyze the contact structure, you need to sort of vary the surface inside the 3 manifold, and this is where you have to start studying what happens, and the thing that controls what happens when you're moving these things is called a bypass, and then you sort of arrange this into. So the plan is to arrange all this into a category, which is called the contact category, and then study sort of properties of it.